Hello everyone, the beginning of a new lesson. In this lesson, we will study the solving by graphical method. The graphical method is more intuitive, but it is only can solve by two decision variables. In this lesson, we discuss three topics. We introduce examples, the steps of graphical method, the LP solution concept. Now we introduce some examples. If we need to solve this LP problem in graphical method, the step one is we draw X lines and Y X lines, and they construct the coordinate systems. And then we draw each constraint line. We set this equal to 4. And we draw this line. This line is this equation. And we set this is the second question. 2x2 equal to 12. We draw this line, x2 equals 6. And we draw the third constraint is this line. This line is 3x1 plus x2, 2x2 equal to 8. And we decided that's direction. That direction is this is the dash direction of the constraint. And this is the feasible range. Feasible range is all the feasible solution correct. And then we draw any objective line. Any objective line, we set J is any number. For example, 2, 0, 3, 0, 6, 0, 0, and so on. And we decide the maximum J direction and move the objective line to along the J increase directions. J increase direction is this direction. So we move the objective line on this direction to the feasible boundary, and stop in this. And we cannot move it out to because this is an unfeasible range. So this point is the feasible solution, and the objective function is maximum. So this point is the optimal solution. And we notice that this point is the intersect point of this line. So we solve the equation 3x1 plus 2x2 equal to 8, x2 equal to 6. We solve these equations and we get x1 equal to x2 equals 6. And we put this to the objective function. We get optimum value is 3,600. And this is the optimum solution of this model. So we have solved these questions, or we have solved these problems. Now we see from the example, we concluded the steps of graphical method. Step 1, draw each constraint line and determine the lesser or greater directions or lesser or greater size, and to determine the feasible range. Step 3, draw objective function line. Draw any objective function line. We set J is any number. Step 4, solve the equation to get the optimal solution. Step 5, to determine the optimum objective values. This is the steps of graphical method. Now we introduce example 2 to solve the following LP problem. The model is maximum J equal 4x1 plus 3x2. The constraint is 2x1 plus 3x2 less than or equal to 24. 3x1 plus 2x2 less than or equal to 26. We first draw the axis and the y-axis on the plan, which is the rectangular coordinate system. And then we draw each constraint of line. We set this is equal to 24, and we draw this line 2x1 plus 3x2 equal 24. And we draw the second constraint line 3x1 plus 2x2 equal to 26. And we determine the less than direction. Less than direction is in this direction, So we get the feasible range is this range. This is the feasible range. And then we draw any objective function. We set J equals 0. We can draw this line. And determine the maximum J directions is this direction, increase J, and we move objective line along this direction. Move objective function line and continue move to the feasible boundary, and we get this point. To this, we do not move it to 2 because if you move away, the solution is infeasible. So this point or this solution is the maximum solution or optimum solution. Similarly, we solve the equation of these equations. Solve these equations, we get x1 equals 6, x2 equals 8, and put this solution to the objective function. We get optimum objective function is J equals 13.6, and this is the optimum solution and the optimum value of this model. So we solve this model. And we see another example, example 3. Example 3 is similar to the former 2 examples, so we introduce rapidly. We draw each of these constraint line. Constraint line we set equal to 14, set equal to 13, and draw this line and this line, and we determine the feasible range, and this is the feasible range. And we join objective line, set J is 0, and determine the increase J directions. This is the increase J directions. We move the objective line along these directions to the boundary of feasible range, and we get this point. And this point is feasible range, and the objective is maximized. So we solve these equations. Solve this equation, and we get the solution is x1 is 15, x2 is 10, and we put this solution to the objective function. We get optimum value is J equal to 18.5. This is the optimum solution and the optimum value of this examples. Example 4, we see this example. Why do we introduce this example? We notice that the objective function is not maximum and it is minimum j equal x1 plus 2x2. And the constraint is or is greater than or equal to rather than less than or equal to. So we need to solve these questions. We first draw x1, x2 line and they construct the coordinate system. And then we join each constraint line. We set this equal to, and we join each line. This is the first line, constraint line, and 2 line. This is line, and this is the third constraint line. And we determine the greater than, and this is the greater than. So this is the feasible range. And we join a objective line. We set j is 0. J is 0 and equal to x1 plus 2x2. And we join this line on this. And we denote the minimized direction. Minimized direction is decrease direction. Decrease direction is this direction. And then we move the objective line around the minimized direction to the boundary of feasible range. We get this point. The point is the minimum minus j and is feasible solution. So this is the optimum solution, and we get the optimum value. So we notice that in the above four examples, there are unique optimum solution, but not all linear problems has unique optimum solutions. We introduce example 5. Example 5, the model is maximum j equal 3x1 plus 2x2. And we notice that the objective function is parallel to this line, and this line is the constraint. So if we move the objective line to the feasible range boundary, then the objective line is inside the constraint line, and this is the segment. And segment solution is all the maximum j and is all feasible range. So this LP problem has multiple optimum solution. And in this segment, any points achieve the maximum j equal to 18. So we call this LP problem has multiple optimum solution. We continue to introduce example 6. No optimum solution. We see this model. We join the graphic. This is the constraint line and less than 4. So it's in this range. And we join a objective function. Objective function is x. And we find that the j is increased infinitely. So in this model, the constraint do not prevent improving the value of objective function j infinitely in the favorable direction. So we say that this problem has unbounded solution and it has no optimum solution. We see another example. We notice that in this model, these three constraints, we determine this range. And the four constraints determine this range, this size. And we show in this example, the feasible range of these two areas has no intersection. These two areas has no intersection, so it has no feasible solution. So this problem has no optimal solution. So in these two examples, we know the problem may be unbounded solution. It has no optimal solution. The problem has no feasible solution. It may be no optimal solution. Okay, from the above examples, we conclude the LP solution concept. The terminology of solution of the model. A feasible solution is a solution for which all the constraints are satisfied. A problem may be many feasible solutions. This is a feasible solution, and there is many feasible solutions. An infeasible solution. Infeasible solution is a solution for which at least one constraint is violated. And this is infeasible solution. Infeasible. A problem maybe have many infeasible solutions. A feasible range is the collection of the feasible solution, and it is possible for a problem to have no feasible solution. An optimal solution is a feasible solution that has the most favorable value of the objective function. Most favorable value of the objective function means we minimize the optimum, retrieve the maximized value, minimum the optimal solution achieve the least or the furthest value. So from the introduction we conclude any linear problem may has four solution cases. Number one is unique optimal solution. Number two is match optimal solution. Number three is no feasible solution. Number four is the unbounded solution. Now we see another solution concept. A corner point feasible. A corner point feasible of which the CP of solution is that lies at a corner of the feasible range. And this is CP of solution, CP of solution, CPF. So a linear problem may have many or finitely CP of solution. The best CP of solution must be an optimal solution. This is the best CP of solution. If the objective function is this line, If the objective function is this line and the optimal solution is many infinitely, and the CP of at least two must be CP of solution. This is CPF solution, and the CPF is no optimal solution. So in these lessons, we have introduced the graphical method to solve linear program, and we introduce LP concept. That's okay in these lessons. Thank you very much.